Topics in post-harvest technology. Refrigeration systems, Part 1. In Part 1, we will discuss some background related to refrigeration, the benefits of refrigeration, and finally, discuss in detail how a refrigeration system actually works to cool a storage facility or room. Refrigeration is the single most important means of preserving produce. Refrigeration has the greatest potential to increase the shelf life of produce of all the post-harvest methods currently used. So what are the benefits of refrigeration? It reduces respiration. It delays ripening. It delays softening, textural, and color changes. It reduces moisture loss. It slows the growth of spoilage organisms on our produce, except in those relatively few cases where the produce is being attacked by microbes that also grow well at cold temperatures. These microbes are known as psychrotrophs. It delays undesirable growth in storage. For example, the production of sprouts from potatoes and the growth of shoots and roots from onion bulbs. Cold temperatures also reduce the rate of lengthening of asparagus spears. Since refrigeration is so important, it is necessary to understand how a refrigeration system functions. But before doing that, we need to discuss some background information. Heat always moves from an area of greater concentration to an area of lesser concentration, and this is the second law of thermodynamics. It's called a law because we have yet to observe a case where heat moves from lower concentration to higher concentration. Since we've never observed an exception, the observation appears to be inviolate, and so we refer to it as a law. Something also to consider is that there is no such thing as cold, just a lack of heat. Cold is how we as humans describe a lack of heat in something or in the environment. Cold is in our minds. With heat, it's a substance, it's energy, and we can move it from one area to another. There is no substance called cold that we can move from one area to another. If there's less heat, we perceive it as colder. If there's more heat, we perceive it as hotter. When a liquid freezes or boils, it undergoes a phase change, and a phase change means it goes to a different state of matter. When freezing, it goes to a much less energetic state. Think of a liquid to a solid, and when boiling, it goes to a much more energetic state. Think of a liquid to a gas. By changing the pressure on the surface of a liquid, the boiling point can be manipulated. At a lower pressure, the boiling point of the liquid is lower. At a higher pressure, the boiling point of the liquid is higher. This figure shows the changes in the boiling point of water as affected by pressure. At 760 millimeters of mercury, which is also 1 atmosphere, water boils at 212 degrees Fahrenheit. We call this the boiling point of water at sea level. As you decrease the pressure, that is, as we go from right to left on the graph, you can see that the numbers on the x-axis are getting smaller. The pressure is getting less, and you can see that the boiling point is decreasing. At 4.6 millimeters of mercury, which is a very strong vacuum, water will actually boil at 32 degrees Fahrenheit. At 1 atmosphere, again 14.7 pounds of air pressure per square inch, water boils at 212 degrees Fahrenheit or 100 degrees Celsius. Let's note that during the boiling process, the liquid water stays at 212 degrees Fahrenheit, and the water will remain at this temperature until it is fully evaporated. In a food pressure cooker with an internal pressure of 29.7 pounds per square inch, as opposed to 14.7 pounds per square inch, water will boil at almost 250 degrees Fahrenheit. This means that the food inside the pressure cooker will cook much faster because the water is hotter. However, at Lake Tahoe, which has an elevation of 6,224 feet, and which therefore has thinner air, meaning less air pressure, water boils at approximately 200 degrees Fahrenheit, and therefore it takes longer to cook food. Remember, boiling is the rapid conversion of a liquid to a gas, and it can occur at any temperature. Notice that rapid is underlined because that is a key idea. At sea level, liquid nitrogen boils at minus 320.4 degrees Fahrenheit, and that is certainly not hot. It is super cold, but the liquid nitrogen is still boiling. This further illustrates the idea that boiling is a process that can occur at many different temperatures, not just that of 212 degrees Fahrenheit for water at sea level. Here is a short video to demonstrate the effect of pressure on the boiling point of a liquid. On the left is a vacuum flask containing acetone at room temperature, that is 72 degrees Fahrenheit. On the right is a vacuum pump. Watch what happens when the pump is turned on. Notice that when the vacuum pump was turned on and the air pressure decreased in the flask, the acetone started boiling. When the pump was turned off, the pressure decreased and the boiling stopped. The pump was turned back on, the pressure decreased, and the acetone proceeded to boil again. In the US, a BTU, or British thermal unit, is defined as the amount of heat it takes to raise 1 pound of water 1 degree Fahrenheit, or conversely, it can be thought of as the heat that is emitted when 1 pound of water cools 1 degree Fahrenheit. This is a key idea. The amount of heat used to heat the water is exactly the same amount of heat that leaves the water when it cools. However, when 1 pound of water is boiled at sea level, rather than taking 1 BTU, it takes 970 BTUs to convert that pound of liquid water to a pound of water vapor. This value, 970 BTUs, is referred to as the heat of vaporization for water at sea level. However, the value of the heat of vaporization is going to vary depending on the liquid. So let's get to the actual mechanics of refrigeration. The function of a refrigerator is to absorb heat energy in one location and to release it at another location. That's the function of a refrigerator in a nutshell. In the case of a produce storage room, heat is absorbed from within the storage room and released outside the storage room. By absorbing heat from within the cooler, the temperature within the cooler will be colder, since there will be less heat energy within that cooler space. A refrigeration system consists of a compressor, condenser, expansion valve, evaporator, and refrigerant. This is a schematic showing a refrigeration system. The system starts with a compressor, which is shown lower left. The compressor sends compressed refrigerant to a condenser. The refrigerant then goes through an expansion valve to the evaporator, and from the evaporator the refrigerant goes back to the compressor. When a refrigeration system is activated, the compressor compresses the refrigerant gas, which raises its boiling point. So imagine that the boiling point of a refrigerant is 28 degrees Fahrenheit at 1 atmosphere. But when compressed, the boiling point is raised to 90 degrees Fahrenheit or higher, depending on the compression pressure. The act of compressing the gas heats it, and the pressurized hot gas is moved to the condenser. Notice in the schematic that the condenser is adjacent to the compressor. At the condenser, we have air or water flowing over the condenser coils, and the air or water absorbs heat from the hot refrigerant gas. When the temperature of the hot refrigerant gas is reduced to its boiling point, it will condense. Remember, the boiling point is the temperature at which a liquid rapidly changes from liquid to gas. But it can also be thought of as the temperature at which a gas can rapidly change into a liquid. We then would call it the liquefaction point, but this term is not normally used. Regardless, the amount of energy absorbed or released is the same. From the condenser, the liquefied high-pressure refrigerant then flows or is pumped to the expansion valve evaporator complex. Again, here's the schematic showing the expansion valve with the evaporator, and these are both inside the cooler. The condenser and the compressor are outside the cooler. The expansion valve controls the flow of refrigerant into the coils of the evaporator and also allows a pressure drop on the surface of the refrigerant. So it has two purposes: to control flow as well as to reduce pressure. As the pressure drops, the boiling point of the refrigerant is reduced to a temperature less than that of the storage room. As a result, the refrigerant absorbs heat and begins to boil in the evaporator coils. Remember that boiling is an energy-intensive process, so as the refrigerant boils, it continues to absorb energy from its surroundings. In the storage room, air is drawn over the evaporator coils by a fan, and there is a heat exchange at the surface of the coils. The boiling refrigerant absorbs heat from the air, thus cooling it. As it boils, the refrigerant turns back into a gas, and this low-pressure gas moves back to the compressor where the process starts again. Again, here's the schematic. So the pressurized refrigerant is liquefied in the condenser. It is then pumped or flows through the expansion valve. As it passes through the expansion valve, there is a pressure drop as it passes into the evaporator coils. Due to the pressure drop and the temperature difference between the boiling point of the refrigerant and the air in the room, the refrigerant will start boiling. As it boils, it will cool the air in the storage room. The liquid refrigerant becomes a gas again. That gas then moves back to the compressor, and the process repeats. So, heat from within the storage room has been absorbed by the refrigerant. Where does the heat go? The heat is released at the condenser, which is located outside the storage room. Air or water flowing over the condenser absorbs the heat that was in the storage room. So, yes, in the storage room, usually we're just blowing air, storage room air, over the evaporator coils. But outside, we use either air or water to absorb that heat. Heat that was in the storage room has now been released outside the storage room. However, since nature does not like energy imbalances, that released energy will try to move back into the storage room. To reduce the rate of return of heat back into the storage area, the walls and ceiling of the storage room are insulated. By definition, an insulator slows heat movement from one location to another, and the more effective the insulator, the slower that movement. The effectiveness of an insulator is indicated by its R value, the units of which are indicated. What you really need to keep in mind is that the higher the R value, the better the insulator will be. For example, fiberglass bats have an R value of 3.32 per inch, while polyurethane board has an R value of 6.25 per inch. That means that polyurethane board is about twice as effective an insulator as is fiberglass. However, if you look at a single pane glass window, single pane glass has an R value of only 0.1, indicating that glass conducts heat very readily. There is no perfect insulator, but some insulators are better than others, as has been mentioned. When building a storage facility, the cost-to-benefit ratio of insulation must be considered. However, the recommendation would be to insulate storage rooms very well, even if this is expensive, as in the long run, much money will be saved on cooling costs. Temperature and total heat energy should not be confused, as temperature only indicates the heat concentration in a specific substance at a specific location at a specific time. Temperature and heat are really not the same. Temperature is a scale, heat is energy. Temperature does not consider the substance that is containing the heat. For example, 1 pound of iron at 100 degrees Fahrenheit contains about only 1/9 the heat energy contained in 1 pound of water at 100 degrees Fahrenheit, as water has a much greater capacity to absorb heat than iron. Another way to look at this is that 1 BTU will raise 1 pound of iron 9.1 degrees Fahrenheit, but 1 pound of water only 1 degree Fahrenheit. So again, temperature can erroneously indicate more heat energy in a substance than is actually contained within. So what are the takeaways? Of all the post-harvest methods used, refrigeration has the greatest potential to increase the shelf life and maintain the quality of produce. A refrigeration unit manipulates the boiling point of a refrigerant such that it boils, absorbing heat, and is later re-liquefied to release the heat. A refrigeration unit absorbs heat at one location and releases it at another. Heat always moves from an area of greater concentration to an area of lower concentration. Insulation is used to restrict, that is, slow heat movement back to the location where it was initially absorbed. The major components of a refrigeration unit are the compressor, condenser, expansion valve, evaporator, and refrigerant.